Let's talk about hexadecimal integers. Hexadecimal numbers is a number system that based on 16. Now, why 16? Why not 9? Why not 8, right? Those are all valid number bases. However, 16 base numbers are special because each hexadecimal digit can be represented by 4 bits of binaries. So very often, because when you are dealing with numbers with assembly language, when you're doing debugging, etc., when you display the content of a location, very often instead of displaying the binary numbers, it's going to display hexadecimal numbers, because hexadecimal numbers are much shorter, right? There's no really long zeros and ones, right? It takes up only 25% of the space a binary number would take. So and so that's why very often you see hexadecimal numbers used to represent underlying binary numbers, and they're really easy to convert from one to another. So hexadecimal, hex means 6, decimal means 10, so it's a 16 base number system. So if you look at the binary, and the decimal number here is just for reference, right? So pay attention, especially between binary and hexadecimal. So it starts from 0, okay? So the number 1 is represented by 1, 2 by 2, right? All the way it goes to 9. At number 9, that's when the decimal number system runs out of digits. So it's going to carry over to 10. It becomes 10, right here. However, in a hexadecimal number system, there are 16 digits, right? From 0 to 15. So how do you represent 10? So the hexadecimal number system uses the letter A to represent 10, B to represent 11, C to represent 12, and so on and so forth, and F to represent 15. And as you notice, at number 15, the binary representation is 1, 1, 1, 1. It utilizes all 4 bits. That means you can map any 4 bits of binary number to a single digit of hexadecimal numbers. And for that reason, it is, hexadecimal number can be used to simplify the display of binary numbers. Okay, so for example, this long binary numbers, right? You basically divide them into 4-bit chunks, and you can translate each chunk into a hexadecimal digit, and this will translate into 16A794. As you can see, this number is a lot longer than this number. So how to convert hexadecimal numbers to decimal numbers? And we use the exact same formula as we used before, right? With the hexadecimal number from right, the least significant digit to the most significant digit from right to left. And the first place value is 16 to the power of 0, and which is 1. And then the next one is 16 to the power of 1, that's 16. 16 to the power of 2, which is 256, and so on and so forth. And then you basically take the digit in a place, multiply by the place value of that digit, and you add them all up, just like what we did with decimal, just the same as what we did with binary numbers. For example, the hexadecimal number 1234, it equals to 1 multiplied by 16 to the power of 3, 2 multiplied by 16 to the power of 2, and so on. And you have 4,660 in decimal. So here's a quick exercise. What does 3BA4 equals? Right? And you basically 3 multiplied by the place value of 3 is 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3. Right? 3 multiplied by 16. B is actually in decimal is 11. Right? As we know, A is 10, B is 11. So you use 11 multiplied by 16 to the power of 2. Now A in hexadecimal is the same as decimal 10. So 10 multiplied by 16 to the power of 1. And here's a 4 multiplied by 16 to the power of 0. And you get 15,268. Now converting decimal to hexadecimal, it's the same procedure as converting decimal. Let's see. No, I think that's a typo here. It should say the same procedure as converting from decimal to binary. The only difference is that, you know what? Let me go ahead and fix the PowerPoint. Okay. So let's say we have a number 422, right? 422, let's divide that by the number system space, which is 16. And you get a quotient of 26 and a remainder of 6. And then you take 26, you divide that by 16, you get a quotient of 1, and the remainder is 10, which is the letter A. And you divide 1 by the number of 16, and you get the quotient of 0, the remainder of 1. And then you write the number from bottom up, that would be 186. So the only difference between converting decimal to binary and decimal to hexadecimal is that instead of dividing a number by 2, we're dividing the number by 16. So how do you add two hexadecimal numbers? And you know, it's the same. Let's say we're adding this number, hexadecimal number with this number, and you work from. I think this example here is adding 1, 2, 3, 4, 4 pairs of hexadecimal number. So what you do here, A is 10, B is 11. A plus B is 21. And 21 is over 16, right? So you cannot represent the number 21 with a single hexadecimal digit. So you carry 1 to the digit to the left, which represent the 1 here represents 16, right? And then 21, you carry over 16 and you have a remainder of 5. And then you write down 5 here, okay? And then here's 1 plus 6 plus 4 is 11, which is the letter B. Okay. Now let's take a look at this. A plus 8 is 16. And it's just over the last digit, 15, which is, I think it's F, right? And in the hexadecimal number. So you have 1, 0. And then you have 5 plus 2 plus 1, which is 8. And it's 8, 0. Now, this 2 addition doesn't make any sense, right? For decimals, decimal numbers, but they make perfect sense with hexadecimal numbers. In here, A plus 5 is 13. 13 is letter D, and you carry over a number 1, 1 plus 2 plus 4. You don't carry over, sorry. So 8 plus 5 is 13, which is the letter D, and it did not go beyond 16. It does not go beyond 15, which is the last hexadecimal number. So there's no carryover. So 2 plus 4 is 6. And in here, 6 plus 2 is 8. 3 plus 4 is 7. Now this, because none of these numbers gets beyond number 9, so they look exactly the same as decimal number addition. So it's a pretty important skill that you need to learn how to, add and subtract the address of variables and instructions, because in assembly language, not only the value of a lot of numbers is being displayed as hexadecimal numbers, the address of variables are also being displayed as hexadecimal numbers. So, for example, let's display an integer. Integers very often use 32-bit to represent an integer. So you have an address, and then you can take a look at the next 32-bit to get the integer value. And then to get to the next number, you have to skip you have to advance, right? Basically add the 32-bit to the address. So that involved with learning how to do add and subtraction of hexadecimal value is kind of important. So let me illustrate what I mean here. Let's see if we have a address A, B, 1, 2, F, C. Okay, and in here we have 4 bytes, 32 bits, right? And then you will know if you add this address, right, with 4, because the address is by bytes, is referencing bytes. So you can add 4, right? And then that will get you the next address. Okay. Okay, how about subtraction? It's the same way as in binary and as in decimal number. Okay, let's see. We're going to subtract the number A2 from the number C6. Okay, so 6 minus 2 is 4. Straightforward. C is what? Well, C is 12, right? A is 10, B is 11, C is 12. So C minus A, which is 10, you get 2. So it's 24. What about 75 minus 47? Well, you need to borrow, because 5 is smaller than 7, you need to borrow 1 from the next digit, from the next place. And when you borrow 1, that's equivalent to the number 16, right? When you borrow 1 in the decimal system, that's 10. When you borrow 1 from a binary system, that's 2. And the 16, you borrow 1, you get 16. So 16 plus 5 is 21. Okay? So 21 minus 7. It would be, let's see, it would be 14. Okay, 14 would be E, the letter E. Okay, now here 7, 1 is already landed over earlier, so it becomes 6. 6 minus 4 is 2. So if I ask you, the address is this, for variable 1 is this, the address of next variable after this variable 1 is this. How many bytes are used by variable 1? So with this question, you basically subtract variable 1's address, right, from the next address. Now, remember, when you do that, you end up with bits, right? But like I said earlier, the smallest unit of addressable memory location is a byte. So you need to subtract this first number from the second number and divide that by 8. And then you'll get the number of bytes used by variable 1. So 8-bit will make a byte. Each byte has 8 bit. 16-bit is called a word. 32-bit is called a double word. And a 64-bit is called a quad word. Now you can use 8-bit or 16-bit, 32-bit, or 64-bit to represent numbers. So let's assume that we only look at positive numbers, right? So for a byte, how many numbers it represents? for a byte with 8 bit is 0 to 255. And I'll show you why. Okay. So let's see, we have 8 bits, right? So the smallest number is 0, 0, 0, 0, 0, 0, 0, 0. Okay? The highest number is 1, 1, 1, 1, 1, 1, 1, 1. Now, you can calculate this number by 1 multiplied by, 1 multiplied by 2 to the 7 plus 1 multiplied by 2 to the 6 plus, and so on. Well, an easier way to, the place value is from 2 to the 0 to 2 to the 7, right? You can kind of imagine, let's say, if we have another bit, let's say we have 9 bit, right? So the next one, so this is the biggest number, right? So if you plus 1, it will become 0, 0, 0, 0, 0, 0, 0, 0, and then the last one you carry over 1, right? And then you become 1. And imagine we have 9 bit, and that number would have been 2 to the 9, right? But we don't have 9 bit, we only have 8 bits. So the biggest number represented by an 8 bit binary number is 2 to the power of 9. No, 2 to the power of 8, sorry. The 9th bit is 2 to the power of 8. That will be minus 1, right? And as you can see, that would be 255. So 1, 1, 1, 1, 1, 1, 1, 1 is 255. Okay, so for a unsigned word, it could used to represent number from 0 to 65,535. Or 0 to 2 to the 16 minus 1, and so on. So what is the largest unsigned integer that can be stored in 20 bits? So the 20 bits, the highest placement value is 2 to the power of 19, right? So I would say so if you have 20 bits, which we don't use in computer we only use the multiply of 8, a byte. But let's just assume some special computer use 20 bits to represent some number. So it would be, the placement value would be from 20 bits, right? From 2 to the 0 to 2 to the 19th, right? So so the biggest number when all the bits are 11, that would be 2 to the power of 20 minus 1. So that would be the largest number, a 20-bit binary that number can represent. Okay, signed integers. I think let's talk about that in the next video.